In this module, we are going to learn about inferential statistics. Inferential statistics has two branches. These are estimation and hypothesis testing. In this module, you will learn what is meant by a statistical hypothesis and the procedure for testing hypothesis about single population means using alternative methods, particularly the rejection reason method and the p-value method. You would also learn about the types of errors which are inherent in such tests and how to measure the probability of such errors. We shall also try to learn about how we can calculate the power of a test and how sample size influences error probabilities. And in the end, we will discuss about the importance of taking care in the interpretation of test results. We may be interested in the parameters or characteristics of a population when making some decisions that require values of those parameters. If the parameter value is unknown, we can take a sample from the population and obtain a numerical estimate of the parameter. In other situations, a decision has to be made about which of the two conflicting claims about the parameter value is plausible. The process of separating the possible conclusions of an experiment into two disjoint sets and using the theory of probability to choose one set or option over the other is known as hypothesis testing. The technique of hypothesis testing can be used to ascertain the validity of two conflicting claims. The objective is to decide which of the two contradictory claims about a parameter is to be rejected. For example, we may wish to test the claim that a new vaccine is more effective than the one currently in use. So let's look at a statistical hypothesis. A statistical hypothesis is basically where we have always a pairs of opposing or contradictory hypothesis. One is called the null hypothesis and the other is called the alternative hypothesis. The null hypothesis is the hypothesis to be tested. It is the hypothesis of no change or no improvement or no difference. It is a claim about the value of a parameter or the values of several parameters or even about the shape of a population. The null hypothesis is tested against the alternative hypothesis, which offers alternative values of the parameter. A random sample is drawn from the population of interest and sample data is examined to see whether the evidence is strong enough to enable us to reject the null hypothesis in favor of the alternative. If the sample evidence does not strongly support the alternative, we cannot reject the null hypothesis. This does not mean we accept the null hypothesis. The null hypothesis continues to be plausible if not rejected. At the same time, rejecting the null hypothesis does not prove that it is false. Let's look at null and alternative hypothesis in some more detail. Let theta denote the parameter of interest. Now this may be the average monthly sales or average productivity or average wages or even difference of wages in organized and unorganized sectors, or it could be the proportion of visitors to a shopping center who actually make a purchase, etc. So let theta 0 denote the value of the parameter as the initial claim under the null hypothesis. This is also known as the null value. The null hypothesis is then stated as H0 or H0 could be written as theta equal to theta 0. It is the hypothesis of status quo. The possible alternative hypotheses are: 1. Alternative hypothesis H1 could be written as theta greater than theta 0, or second, h1 could be theta less than theta 0, or the third way could be h1 is theta not equal to theta 0, which means either theta is less than theta 0 or theta is greater than theta 0. Now these are known as upper-tailed, the lower-tailed and the two-tailed tests respectively. The way we state the alternative hypothesis has implications for the null hypothesis. Thus, if our alternative hypothesis h1 is theta is equal to or theta is greater than theta 0, then our alternative hypothesis means that theta is less than or equal to theta 0, which is an upper-tailed or right-tailed test. Similarly, if we write h1 where theta is less than theta 0, then it implies that our null hypothesis h0 is theta greater than or equal to theta 0, which would be a lower-tailed or left-tailed test. And h1, if we write equal to theta not equal to theta 0, then it would imply that our null hypothesis h0 is theta equal to theta 0, which is a two-tailed test. To test the null hypothesis, we need to first draw a random sample from the population and then apply a decision rule that uses the sample observations. It is important to set up the hypothesis correctly in the light of the problem situation. The alternative hypothesis is determined before any data are collected. It is based on the belief about the possible range of values of the parameter in the event the null hypothesis is not supported by the sample data. For the one-sided test, we would consider the alternative hypothesis to be plausible if sample data suggests the true value of the parameter is much higher than the null value, which is an upper-tailed test, or much less than the null value, which is a lower-tailed test. Similarly, in the two-tailed test, the alternative hypothesis is considered true if the sample data suggests the true value of the parameter is much higher or much lower than the null value. That means the true value is significantly different from the null value. Let us now look at the test procedure in this section 3.2. Test procedure is the rule for deciding whether to reject or not reject the null hypothesis based on sample information. The test procedure has two components. The first is a test statistic derived from the appropriate sample statistic, which is a function of the sample observations. Second is the rejection reason, which consists of those values of the test statistic for which the null hypothesis is rejected in favor of the alternative hypothesis. The decision rule for deciding whether to reject or to not reject the null hypothesis depends on the specified rejection reason. Let us understand the steps in the tests of hypothesis. The first step is that identify the parameter, say for example theta, which could be population mean mu or population proportion p or variance sigma square, etc. The second step involved is determine the null value theta 0 from the given problem. So it means specify theta 0. The third step is state the null hypothesis, which means write down h0, which could be written as h0 where we may say theta is equal to theta 0, and the appropriate alternative hypothesis as required by the given problem, which as said earlier could be a one-tail or a two-tail test, and which we know could be h1 where theta may be greater than theta 0, or h1 where theta may be less than theta 0, or h1 where theta is not equal to theta 0. Now give the formula for the test statistics. This is our fourth step, which could be a z test or a t test or a chi-square or an f test. The next step, fifth step, is calculate the applicable sample statistics theta hat from sample observations, which could be denoted as x bar or x by n or s square, etc. The sixth step is calculate the value of test statistic, that is zt chi square f, using calculated value of the sample statistic. The next step, seventh, is the state the rejection reason using desired critical values of the test statistic. The critical values of the test statistic and the rejection reason will both depend on how the alternative hypothesis is defined. I am sure you can all understand this. Let me elaborate and mention the next step, which is step 8. Apply the decision rule to reject the null hypothesis if the calculated value of the test statistic falls in the rejection reason, and do not reject otherwise at the alpha level of significance, where alpha is the level of significance. The last step, ninth, is state the conclusion in terms of the problem posed. It is interesting to note that the sample statistics and the corresponding test statistics used in the test of hypothesis are the same as those used in the estimation problems. Let's now move on to the types of errors and significance level of the test in this section 4. To test the null hypothesis versus the alternative hypothesis, we select a random sample from the population in focus and use the sample observations to reach the appropriate conclusion. Although the method of random sampling is likely to result in a representative sample, this does not rule out the possibility of selecting an unrepresentative sample. The probability of drawing such a sample may be small but not impossible. Now, due to sampling fluctuations, an unusual sample may result in rejecting a null hypothesis when in fact it is true. Similarly, an unrepresentative sample may result in failing to reject a false hypothesis or false null hypothesis. Now, these are the two types of errors associated with hypothesis testing. So, we have type 1 error when a true null hypothesis is rejected. Similarly, we have type 2 error results when a false null hypothesis is not rejected. The two types of errors are shown schematically or systematically in table 1. You can see in this table we have the decision, we have the hypothesis S0 true, S0 false, and the decisions are reject S0, which is a probability, and do not reject S0 again in terms of probability. Type 1 error is also denoted by alpha, or alpha you may call as the type 1 error. If we have the correct decision, it is 1 minus alpha, and then we have the correct decision 1 minus beta, and type 2 error is beta. So from this table you can see type 1 error occurs when we reject the null hypothesis when it is true, and type 2 error occurs when we do not reject the null hypothesis when this null hypothesis is false. A good test procedure is one in which the probability of making either type of error is small. The probability of either type of error is determined by the choice of the rejection reason. The rejection reason itself is determined by the choice of the critical values of the test statistic. So, probability of type 1 error is fixed by the choice of the critical, that is the cutoff values, and the rejection reason. So, the probability of type 2 error also requires knowledge of the alternative parameter value. We denote probability of type 1 error by alpha and the probability of type 2 error by beta, as I said earlier also. Consequently, you will find that the probability of making the correct decision of not rejecting the true null hypothesis is 1 minus alpha. Similarly, the probability of making the correct decision of rejecting the false null hypothesis is 1 minus beta. These probabilities are shown in brackets in table 1, which you can note. And note that alpha plus beta is not equal to 1. Tests using samples will result in two types of error because of sampling fluctuations, which could be reducing one type of error results in an increase in the other type of error. So increasing the sample size can help reduce both types of errors simultaneously. Now, only way to eliminate both types of error is by examining the entire population. Let us first see how we can control the probability of type 1 error, that is alpha. For illustration, we will consider the test for a single population mean. Let the hypothesis be H0 mu equal to mu 0 versus alternative hypothesis H1, which is mu is greater than mu 0. This is an upper tail test and the null value is mu 0. A random sample of n observations is selected from the population and the sample statistics x bar is calculated. Under the assumption that the null hypothesis is true, the distribution of sample means of sample size n from the same population is centered at mu 0, since expected value of x bar is equal to mu 0. So if the population is normally distributed with known variance sigma square, or if the sample is large, then the sampling distribution of means is also normally distributed with the mean mu 0 and variance sigma square by n. The test statistics in that case is standardized variable z and is equal to x bar minus mu 0 upon sigma by under root n and is distributed normally with mean 0 and variance 1. The probability of type 1 error is controlled at the level alpha. The critical value z alpha is selected by fixing alpha at the desired level. In our figure 1a, z alpha is selected so that alpha area is in the upper tail of the distribution, which is shown by the shaded area. The remaining area under the z curve to the left of z alpha is 1 minus alpha. I am sure you can see it clearly from the diagram. The decision rule says that if the calculated value of the test statistics ZC is such that ZC is greater than or equal to Z alpha, then reject the null hypothesis H0. If ZC is less than Z alpha, then do not reject the null hypothesis H0. The rejection reason therefore is of Z, where ZC is greater than or equal to Z alpha. Now, the calculated value of the test statistics ZC is equal to x bar minus mu 0 upon sigma by root n, and it depends on the value of x bar given mu 0, sigma and n. For different samples, we are likely to get different values of ZC. It is a matter of chance which sample is selected from results in a particular value of ZC. If the null hypothesis is true and ZC is less than Z alpha, then we make the correct decision of not rejecting the null hypothesis H0. Probability of making the correct decision of not rejecting true null hypothesis is 1 minus alpha. The corresponding to Z alpha, the cutoff value of x bar is alpha is equal to mu 0 plus Z alpha into sigma by root n. The rejection reason is therefore equal to x bar greater than or equal to mu 0 plus Z alpha into sigma by root n. Now, due to sampling fluctuations, it is possible to get an unrepresentative sample which has a high mean value, and we reject the null even though it is true, which means we are committing type 1 error. So, we are committing type 1 error with the probability P, which is of x bar greater than or equal to mu 0 plus Z alpha into sigma by root n, and is equal to alpha as shown in figure 1b. So, what cutoff value of ZC or X alpha bar we use to define the rejection reason will depend on what is our tolerance for type 1 error. The critical value Z alpha is selected by fixing alpha. If ZC is greater than ZA or Z alpha, we say that the true population mean is significantly more than the null value mu 0. The level of significance of the test is alpha when we use the level or minus alpha test. Commonly used levels of significance are 0.05, 0.01 and 0.10. Corresponding Z critical values are 1.645, 2.33 and 1.28 respectively for the upper tail test. Similarly, we have the level alpha tests for the lower tailed and two-tailed tests. You will find that in figure 2 we illustrate these tests. In the lower tail test, Z of at level 0.05 is equal to minus 1.645 and Z at 0.001 is equal to minus 2.33 and Z at 10% level, which is 0.10, is equal to minus 1.28. In the two-tailed tests, the rejection region is distributed equally in the two tails of the distribution. The critical values are then, in a way I am sure you can recollect, is they are Z for 5%, which is 0.025, is equal to plus minus 1.96, Z for 0.05 is plus minus 1.645 and Z for 0.005 is plus minus 2.58 for respectively 5%, 10% and 1% levels of significance. Now, reducing the rejection reason reduces alpha, but this increases the probability of type 2 error. So, in the test procedure, we try to minimize the more serious of the two errors. If the hypotheses are set up properly, then the more serious error will be type 1, as this can be controlled and the probability alpha known. Determination of beta requires knowledge of the distribution of the sample statistic when H0 is false. Let's take an example. Example 1. An oil company claims that the sulfur contents of its diesel fuel is at most 0.15%. Now, to check this claim, the sulfur contents of 40 randomly chosen samples were determined. The resulting sample mean and standard deviation were 0.162 and 0.040 respectively. Using the 5% level of significance, can we conclude that the company's claims are invalid? Let's see the solution. In the solution, we can see that since the sample is large, sampling distribution of X bar is approximately normal by central limit theorem. Now, N is 40, mu 0 we know is 0.15, X bar is 0.162, S is 0.040. And what is the null hypothesis? It is that mu is equal to 0.15 versus alternative hypothesis that mu is greater than 0.15. The level of significance we have chosen is 0.05. So, what is the Z value? It is equal to 0.162 minus 0.15 divided by 0.04 upon under root 40. On simplification, it comes out to be 2.37. The critical value is Z005 is equal to 1.645. So, what we find is that R is equal to, which is Z, and Z is greater than 1.645. So, since 2.37 is greater than 1.645, we reject H0 at 5% level of significance. We can conclude that the company's claims are invalid. Let's take another example. An aircraft manufacturer needs to buy aluminum sheets of 0.05 inches thickness. Now, thinner sheets would not be appropriate and thicker sheets would be too heavy. The aircraft manufacturer takes a random sample of 100 sheets and finds that their average thickness is 0.048 inches and their standard deviation is 0.01 inches. Should the manufacturer buy the aluminum sheets from his supplier at 5% level, 1% level of significance? Again, we can see that n is equal to 100, mu 0 is equal to 0.5 inches and x bar is equal to 0.048 inches and s is equal to 0.01. Our null hypothesis is that mu is equal to 0.05 versus the alternative hypothesis that mu is not equal to 0.05. The alpha level we have selected is 0.05 and 0.01, or they are also given to us in a way. So since this is a two-tailed test, we can see that z value of at 0.025 will be equal to plus minus 1.96. So this 0.025 is one tail area, the total two tail area is 5%. And similarly, z at 0.005 is equal to plus minus 2.58. The calculated value of test statistics now is equal to ZC equal to 0.048 minus 0.05 divided by 0.01 upon under root of 100. Now on simplification or on calculation of these, it comes out to be minus 2. Comparing with the critical values of the test statistics, this modulus 2 comes out to be greater than 1.96 and modulus 2 is less than 2.58. Therefore, the null hypothesis is rejected at 5% level of significance but not rejected at 1% level. So if the aircraft manufacturer uses the alpha level 0.05, then the decision should be to not buy the aluminum sheets from his supplier. The decision is reversed at alpha level of 0.01. Let's now try to understand what is type 2 error and power of a test. The distribution of the sample statistic is always centered at the true value of the parameter. Let us consider the upper tail test, and H0 is where mu is equal to 100 versus H1 is where mu is greater than 100. The population is normal with sigma equal to 10. The random sample of size 12 has a mean of 105. Then ZC comes out to be equal to 2.24. So if alpha level of the test is 0.01, then Z alpha is equal to 2.33 and we do not reject null hypothesis H0. The cutoff value of the sample mean is 100 plus 2.33 into 2.236 and is equal to 105.21. Now let the true mean be mu1 equal to 105. The sampling distribution would be centered at 105. The probability that sample mean is less than cutoff value so that H0 mu is equal to 100 is not rejected when alpha is equal to 0.01 and cutoff value is 105.21. So when mu1 is equal to 105 is the probability of type 2 error. Therefore, we can write down that beta of 105 is equal to probability that x bar is less than 105.21 when true mu is 105. And this is equal to probability that z is less than 105.21 minus 105 upon 10 divided by under root 20, which is nothing but 5 of 0.09 and is equal to 0.5359. Now suppose that the true mean is 104, then this beta 104 will be equal to probability of z less than 105.21 minus 104 upon 10 divided by under root 20, which is 5 of 0.54 and is equal to 0.7054. Similarly, if the true mean is 106, then we can find out beta 106 and it comes out to be equal to 0.3632. So similarly, we can calculate the probability of type 2 error for different alternative values of the true mean if the null value is false. Notice that the cutoff value of sample mean, which is x bar alpha or x alpha bar is equal to 105.21, is determined by z alpha and mu 0 for selected level alpha. But if beta of mu 1 varies from value of mu 1, it is possible to calculate beta only if the alternative value of the parameter is known. Now figure 3 illustrates type 2 error for the upper tailed test. You can see we have this figure 3 where we have the probability of type 1 error alpha and type 2 error beta. It can be observed that as the true parameter value is further away from the false null value, smaller is the probability of type 2 error. Closer mu 1 is to mu 0, greater is beta, and less is the ability of the test to distinguish between false null hypothesis and the true alternative. The ability to make the correct decision of rejecting the false null hypothesis is reflected in the probability 1 minus beta. The probability 1 minus beta is called the power of the test, as it is the probability of being able to distinguish between the null and alternative values of the parameter. So students, now let alpha is equal to 0.005, then z alpha is equal to 2.58 and x alpha bar or x bar alpha is equal to 100 plus 2.58 into 10 by root 20 and comes out to be equal to 105.77. Now we calculate beta mu 1 as above and we find beta for 105 is equal to phi of 0.344, which is equal to 0.6331. Similarly, beta of 104 is equal to 0.7764 and beta of 106 is equal to 0.4602. A comparison of results for alpha equal to 0.01 and alpha equal to 0.005 illustrates how beta decreases as alpha increases and is also shown in table 2. So we have the null hypothesis where we have mu 0 equal to 100 and we have alpha equal to 0.005 and alpha equal to 0.010. In our second column, we have the alternative hypothesis of mu 1 equal to 104 and then of 105 and then of 106. And we have these different calculated values of betas for 104 and beta for 105 and beta for 106. So this table basically shows the relationship between the probabilities of type 1 error and type 2 errors. The two entries in each of the second, third and fourth column shows how type 2 error probability declines with increase in significance level of the test. So as we try to reduce one type of error, we run the risk of increasing the other type of error. The second and third rows show how for given significance level alpha, the probability of type 2 error declines as the distance between the null value and the alternative value of the parameter grows. So the power of the test 1 minus beta increases accordingly. The example of an upper tail test has been used. Similarly, for a lower tail test and for a two-tailed test, we can similarly calculate the cutoff values of the sample mean and find probability of type 2 error and power of the test for given level alpha of the test. How we calculate beta for Z test. Now, in this section, we will find that when the sample is large, n is greater than or equal to 40, or second population is normal with known sigma for any sample size, or when the population is unknown with known sigma but n greater than or equal to 30, we can then use the Z test for single population mean. So our null hypothesis is that mu is equal to mu 0. We can consider the three alternative hypotheses, which is h1 of mu greater than mu 0, where our R is Z such that Z is greater than or equal to Z alpha, and this is equal to x bar such that x bar is greater than or equal to x alpha bar equal to mu 0 plus Z alpha into sigma by root n. So this is our first alternative, and if we have the true value of mu equal to mu 1, which is greater than mu 0, then we can see that beta mu 1 is equal to probability x bar less than x bar alpha. And this you can see on your screen is equal to probability of x bar less than mu 0 plus Z alpha into sigma by root n. And this can be further simplified and is equal to phi of mu 0 plus Z alpha into sigma by root n minus mu 1 upon sigma by root n, and is equal to phi of mu 0 minus mu 1 upon sigma by root n plus Z alpha. So we have similarly the second hypothesis and the third alternative. In the second one we have mu less than mu 0, and what we get is beta mu 1 comes out to be equal to 1 minus phi into mu 0 minus mu 1 upon sigma by root n minus Z alpha. And in our third alternative of where h1 is equal to mu not equal to mu 0, we find that beta mu 1 comes out to be ultimately equal to phi of mu 0 minus mu 1 upon sigma by root n plus Z alpha by 2 minus phi of mu 0 minus mu 1 upon sigma by root n minus Z alpha by 2. So we have Z alpha by 2 as a positive number, and then in the second expression we have minus Z alpha by 2. Now, although the tests for population mean have been used to explain the steps in the hypothesis testing and calculation of beta, the same applies for any parameter theta, where the sample statistics theta hat is normally distributed. The standardized variable theta hat minus theta upon sigma of theta hat has the standard normal distribution, and the Z test is applicable if the sample is large or standard deviation is known when the population is normal. Example 3. A sample of 64 observations is taken from a population with sigma equal to 24. At alpha level of 0.01 test, our null hypothesis H naught is that mu is equal to 300 versus the alternative hypothesis that mu is greater than 300. So if true mean is 310, calculate beta and power of the test. Let's see the solution. So for alpha is equal to 0.01, Z alpha is equal to 2.33. If ZC is less than 2.33, then null hypothesis H naught is not rejected. Then beta 3 or beta of 310 is equal to phi of 2.33 plus 300 minus 310 upon 24 by under root 64, which is equal to phi of 2.33 minus 3.33 and is equal to phi minus 1, which is equal to 0.1587. Therefore, the power of the test is 1 minus 0.1587 and is equal to 0.8413. Let us now try to understand the sample size determination. Firstly, we had fixed alpha and calculated beta. If we wish to reduce beta without increasing alpha, we need to increase the sample size. The required sample size can be derived from the formula for calculation of the beta. In the upper tail test, the null hypothesis is that mu is equal to mu 0 versus the alternative hypothesis that mu is not equal to mu 1, where mu 1 is greater than mu 0 and beta of mu 1 is equal to phi of mu 0 minus mu 1 upon sigma by root n plus z alpha. So let us use z beta to denote z critical values that demarcate the lower tail area beta. Then minus z beta is equal to mu 0 minus mu 1 upon sigma by root n plus z alpha. Rearranging the terms, we obtain n is greater than or equal to sigma into z alpha plus z beta upon mu 0 minus mu 1 whole raised to the power 2. Similarly, for lower tail test, from z beta equal to mu 0 minus mu 1 upon sigma by root n minus z alpha, we get n greater than or equal to sigma into z alpha plus z beta upon mu 0 minus mu 1 whole raised to the power 2. Also, by rearranging the terms for the two-tailed test, we get n greater than sigma into z alpha by 2 plus z beta upon mu 0 minus mu 1 raised to the power 2. The sample size obtained in this fashion will control the two types of error at desired levels. Larger the sample, less is the probability of type 2 error. However, too large a sample is costly. Hence, the optimum size can be obtained by the above calculations which we have shown just now. The method demonstrated here pertains to the test of a single population mean with the null value mu 0 and alternative value mu 1 when the test statistics is the z statistic. This can be extended to any other parameter with null and alternative values theta 0 and theta 1 respectively if the z test is used. However, it is possible to decide the sample size only if beta can be calculated, which means that the alternative value of the parameter is known. P-value and tests of hypothesis. The rejection reason approach leads to rejection of the null hypothesis if the calculated value of the test statistic lies in the tail area, that is critical reason, defined by the critical value of the test statistic. For example, z alpha or minus z alpha or plus minus z alpha by 2. However, this does not indicate how strong is the evidence in favor of the alternative hypothesis. For instance, continuing with the example of the upper tailed test, let ZC is equal to 1.67. Then H naught is rejected at level 0.05. However, the difference between critical value 1.645 and calculated value 1.67 is very small. So instead of 1.67, if the calculated value was 2.3, then 2 H naught would be rejected, but this time with an appreciable margin. In the latter case, the decision is clear-cut, but not in the former case. Furthermore, different conclusions may result from different levels of significance selected by an individual depending on her perception of the consequences of type 1 and type 2 errors. For alpha level 0.05, the null is rejected and not rejected at alpha level 0.01. A p-value gives information about the strength of the evidence supporting the alternative hypothesis. The researcher can use this to draw conclusions at any specific alpha level of significance. Let's define this. The p-value is the smallest alpha value at which the null hypothesis would be rejected. Calculation of p-value depends on whether the test is upper-tailed, lower-tailed or two-tailed. So let ZC denote the calculated value of the test statistics as shown in figure earlier. Then let H naught is theta equal to theta 0. So if H1 is theta greater than theta 0, then p value could be written as p z greater than or equal to zc, which is equal to 1 minus phi ZC, which is upper tailed. Since Z alpha increases as alpha decreases, P value is the value of alpha for which ZC is equal to Z alpha, and it is the tail area to the right of ZC, which is our figure 4a. Now, if H1 is theta less than theta 0, then P value could be written as P Z less than or equal to ZC, which would be equal to phi minus ZC, which is again equal to 1 minus phi into modulus minus ZC, which is a lower tailed value. Similarly, P value is the value of alpha for which ZC is equal to minus Z alpha, and it is the tail area to the left of ZC, which is figure 4b. Now, if we write alternative hypothesis H1 as theta not equal to theta 0, then we have a two-tailed test, and we can write down the P value as probability of ZC or minus ZC greater than or equal to Z, or Z greater than or equal to ZC, which will be equal to 2 phi into minus ZC, which is same as 2 into 1 minus phi modulus ZC. Now, P value is the value of alpha for which ZC is equal to plus minus Z alpha by 2. So that area captured in either lower tail or upper tail, which is figure 4c, for cutoff value modulus ZC is half the P value. So I am sure you can all observe these three diagrams for A, B and C and see how we have tested the upper tail, lower tail and both the tails in these diagrams. Let us now try to understand p-value approach to tests of hypothesis. Now, calculation of p-value depends on whether the test is upper or lower or two-tailed. But once it has been calculated, the decision rule simply requires comparison of p-value with alpha to reach a conclusion. This conclusion or this comparison is independent of the type of test, since we can see that phi modulus z would always be between 0 and 1. So can be written as phi modulus z greater than or equal to 0 and less than or equal to 1 always. The decision rule is illustrated in our figure 5. Now, the decision rule could be that if p-value is less than or equal to alpha, then reject null hypothesis H0 at alpha level. If p-value is greater than alpha, then do not reject null hypothesis H0 at alpha level. So let H0 is equal to theta is equal to theta 0 versus alternative hypothesis H1, which is theta greater than theta 0, or H1 could be theta less than theta 0, or H1 theta not equal to theta 0. So if alpha is between 0 and p-value, then we do not reject hypothesis at level alpha. If p-value is or alpha is between p-value and 1, then reject null hypothesis H0 at alpha level of significance. So you can see we have written this range between 0 and 1, and we have the p-value. So if we are between p and 1, we reject the null hypothesis. If we are between 0 and p-value, we do not reject the null hypothesis. So figure 5 is our decision rule in the p-value approach to hypothesis testing. Let us now talk about the statistical versus practical significance of a test. We basically say that a test is statistically significant if the sample evidence leads us to reject the null hypothesis. This will of course depend on the selected alpha level. In the classical methodology, H0 is rejected if the calculated value of the test statistics lies in the critical region defined by Z alpha or Z alpha by 2 modulus. In the p-value approach, hypothesis H0 is rejected if p-value is less than or equal to alpha. The calculated value ZC is a random variable as it depends on which sample was selected. Since the p-value depends on ZC, therefore p-value is also a random variable. A small p-value indicates the sample statistic is significantly different from the null value. However, even if the difference between the sample statistics and the null value is small, a large sample would result in a small p-value. Hence, even if the difference is not of any practical significance, we are led to concluding that the difference is statistically significant. We should therefore be careful in interpreting the test results, as both ZC and p-value are sensitive to the size of the sample. For large sample, any small departure is detected by the test, even if the difference between the null value theta and the sample statistics theta hat is not of any practical significance. Let us now look at and discuss and try to understand the likelihood ratio principle. Now, this is the third approach to tests of hypothesis and is based on the likelihood ratio principle using the likelihood function. If a random sample of n observations, let's say x1, x2 up to xn, is selected from a population distribution which is which could be denoted as fx given theta, then the likelihood function L of theta given x1, x2 to xn is nothing but the joint probability function of the sample observations. It is also a function of the parameter theta. In the upper tail test, which is H0, where we write theta less than or equal to theta 0 versus alternative hypothesis theta greater than theta 0, we can think of the values theta less than or equal to theta 0 and theta greater than theta 0 as two disjoint sets. So let us denote the two disjoint sets by, say, phi 0, which is a function of theta, and theta is less than or equal to theta 0, and phi 1, which is a function of theta, but theta now is greater than theta 0. So what are the steps in this test procedure? These steps are as follows. First, calculate the maximum likelihood estimate of theta from among the values in phi 0 and substitute in the likelihood function to get the value of likelihood function. This gives us the largest value of the likelihood of theta in phi 0. Similarly, find the maximum value of the likelihood function for theta in phi 1. Then the third step is compute the likelihood ratio statistics value, which could be denoted as lambda and is a function of x1, x2, xn, which is nothing but is equal to maximum likelihood for theta in phi 0 divided by maximum likelihood for theta in phi 1. The last step is reject the null hypothesis H0 if this lambda is less than or equal to k, where the constant k is selected to give us the desired alpha level. The ratio will have a small value if the sample is more likely to have come from a population with theta in phi, and we can reject the null hypothesis in such situations. Tests based on likelihood principal ratio are the best test among all tests, as these minimize beta for desired alpha level. However, construction of the test statistic requires the probability distribution of the population. If the form of the population is known, then the test can be applied even if the sample is not a random sample, which means the sample units are dependent and different sample units have different distributions. The test based on LRP is the best test as it minimizes probability of type 2 error for given level of significance of the test. So now students, after going through all this, let us summarize what we have learned in this module. What we have learned is that tests of hypothesis require setting up of null and appropriate alternative hypothesis, deciding on the test statistic, calculating the value of test statistic using sample observations, and reach a conclusion using the desired level of significance. We have also learned that there are two types of errors associated with tests of hypothesis, which are the probabilities of two types of errors have an inverse relationship, and level of significance of the test depend on the tolerance for type 1 error. Type 2 error, we have said, can be calculated if the alternative value of the parameter is known. Then this too can be controlled by adjusting sample size. Two main methods of testing are the rejection region method and the p-value method. This is what we have learned. We have also learned that the likelihood ratio method is a third alternative which yields results with minimum probability of type 2 error among different methods. Please understand that care must be taken while interpreting the test results. If sample size is large, the test results may lead us to conclude that it is statistically significant. However, the actual difference between the null value and the true parameter value may be too small to be of any practical importance.